Okay, and welcome to the next video in exponentials, where we look at the exponential gradient, a very important concept in this subtopic exponentials, and it's a function which you will definitely see later on in the course. So, in the previous video we looked at exponential functions which had the form y equals a to the x. Now, if we sort of think about the graphs y equals a to the x, we know what form they have. So let's look at y equals 2 to the x. Okay, and let's look at y equals 3 to the x, which will be slightly higher. Now, if I was to look at this, an x against y, an x against y, okay, and if underneath these graphs I looked at how gradient changes over time. So underneath I'm going to look at gradient, which we should remember from pure 1 is dy dx. Then what you'll see is that the gradient of these graphs, it starts here, and as the x values increase, the gradient increases as well. So it will actually follow a very similar pattern. You'll have this sort of shape. Okay, it's the same here, just a bit steeper though. Sorry. Now, if you were to overlay the gradient graph on top of these graphs, what you get is a situation that looks like this. So this here is the gradient graph, which I've just taken from there, and this is the gradient graph which I've taken overlapped on top of that graph. So what you can see is for 2 to the power of x, the gradient graph is below 2 to the power of x. And for 3 to the power of x, the gradient graph is above 3 to the power of x. So that must mean that there's a value between 2 and 3 such that the gradient graph must be on top of the original graph. And there is a value for which that is the case, and it's actually a very special type of base number. And it's called Euler's number, and it has this value 2.71828. Okay? However, it's an irrational number, so we use the value e, okay, and that you can find in your calculator. Now, e to the power of x is a very special exponential. The reason why is because when you differentiate it, it will look exactly the same as the original graph, whereas if you differentiate these two, the equations will not be the same. You will learn how to differentiate exponentials of this form later on in the course, most likely in year 13. So let's just highlight that again. Differentiating e to the x gives you e to the x. So what happens if you just don't have e to the x? What happens if you got e to the x, you know, whatever? Well, if you got e to the kx plus a, anything as a power which isn't just x, then what you do is you differentiate the power and then bring down whatever that is in front of the e. Okay, so if you've got kx plus a, ignore the e for the time being, kx plus a, whatever that kx plus a is, differentiate that using pure 1 differentiation and bring it down in front of the exponential. Okay, now this pattern can be shown for all types of e to the power of x graphs, so it does show, it does work. Okay, however, the reasons for it and the technique behind it is actually year 13 knowledge, where we look at chain rule. So I'm going to show you how this differentiation works. So if you look at question 1a, we're asked to differentiate or find f dash x of these functions. So what I do is I look at the function, I look at the power, and I focus on that. Okay, 2 to 2x, what does that differentiate to? I know that 2x differentiates to 2. And according to the rule which I was just taught here, if 2x differentiates to 2, I'm going to bring that down, that derivative down, and keep the power as it is. When you differentiate derivatives, you do not subtract 1 from the power. That's really important. Okay, next one here. Look at the power. I differentiate that. So minus a half x, if I differentiate that's minus a half, I bring it down in front of the 4 in front of the e, there's already a 4 there, so you're going to get f dash x equals minus 2 e to the minus half x. 3x you differentiate normally, you just get 3. Okay. Final one, you've got f of x equals 2e to the 3x plus 2. So again, I focus on the power of 3x plus 2. I differentiate that in my head. 3x plus 2 differentiated is 3. I bring it down in front of the e. There's already a 2 there, so it's going to be 6e 3x plus 2. Okay. Now, as I said, if you were to go on Desmos or any other graphing software and type in e to the 2x and 2e to the 2x, you'll find that the gradients will match up. Okay, so these results do work. So, final question on the sheet. It's really important that you understand to differentiate this, because you could be asked to find anything once you know the derivative of an exponential, and this is where you can be asked to do it. So question 2, the gradient of the curve y equals e to the 0.5x at the point where it crosses the y-axis. So we need to find the gradient where it crosses the y-axis. So, to find the gradient where it crosses the y-axis, whenever a curve crosses the y-axis, you have to remember x is equal to 0. Okay, so when it crosses the y-axis, x is equal to 0. So we need to find the gradient. We need to find the value of dy dx. For that to happen, we need to differentiate first of all. So you've got e to the 0.5x. Again, focus on the power. 0.5x. Differentiate that in your head. It's 0.5. Bring it down in front of the e. Okay. Now, all you need to do, you've got the gradient function. To find the gradient where it crosses the y-axis, you just sub x equals 0. And when you do that, you get dy dx equals 0.5 e to the 0, which is just 0.5. Okay? And therefore we need to find the equation of the normal at this point. So let's try and understand this carefully. We've got this exponential. We know we found the gradient at where it cuts the y-axis. Okay, so I know the gradient, and I know from pure 1 that the gradient at where it cuts the y-axis is also the gradient of the tangent. So if that's the gradient of the tangent, 0.5, then the gradient of the normal will be the reciprocal of that. So obviously 0.5 is a half, so it's going to be reciprocal of a half, which is minus 2. And the normal, if you remember from pure 1, is a perpendicular line that cuts the curve at that point. Okay, so that's my normal. Right, so I've got the gradient of my normal. I know that the x value will be equal to 0. The y value, well, that will just be equal to 1. Or y equals e to the 0, which is just 1, yep. So I've got everything I need to find the equation of the normal. So I'm going to use straight lines knowledge. Y minus y1 equals m x minus x1. Okay, I'm going to expand the brackets here. And that's the equation of the normal. So that, in essence, is what you could be asked to do with the derivatives of e to the x. It's a really powerful technique. Okay, it's not very difficult. As I said, look at the power, differentiate it in your head, bring down the result in front of the e. Okay, and then you could be asked to do a variety of things: tangents, normals, stationary points, etc. Again, textbook questions are outlined here. Well worth having a go. You will definitely be asked questions on this in the course.